welcome to the course RF transceiver design. We are discussing a transceiver architecture. In last class we have discussed the direct conversion receiver architecture. It is also well known as a 0 IF receiver or a homodyne receiver, where your omega RF is equal to omega LO. We have seen the merits and demerits of the direct conversion receiver. Now we will move little bit further to the another two class which is widely used in RF transceiver design, that is a Hartley and Weaver. So before going to the Hartley and Weaver architecture, we will try to understand the Hilbert transform. So understanding the Hilbert transform is important. What it exactly do, it will add the 90-degree phase shift. So for example, we can write for cos omega ct, if there is a signal A cos omega ct, then we can write A by 2. So, A e raised to j omega ct plus A e raised to minus j omega ct by 2. So, your cos omega ct has a exponential term which is a positive and negative, at which is centered at the omega c, and the amplitude is A by 2. So, same thing, if we try to draw this is a real plane. So, there is a two plane has been done, there is a real plane here and this is a imaginary plane. So, the cos you can easily represent on the real plane. So, if I will draw this is a 3 dimensional, if I will draw the 2 dimensional, then cos omega ct, that is centered at omega c, and this is minus omega c, and the amplitude is A by 2. Now, if we try to write the sin omega ct, A sin omega ct, then it is written as a minus A j e raised to j omega ct plus A j e raised to j minus j omega ct by 2. So, you can see that for negative frequency, because this is imaginary plane, it is a positive j a by 2, and for negative frequency for positive frequency which is a plus j omega ct, it is minus j a by 2. So, this is the amplitude. So, what is the Hilbert transform? So, Hilbert transform can be written as a transfer function of Hilbert transform 90 omega, which is equal to x omega into minus a signum omega. So, what is the signum function? Signum function, so signum function has a, if I write a signum function here, the definition of signum function, that is signum function omega is equal to 1 for omega greater than 0, is equal to 0 for omega is equal to 0, and minus 1 if it is omega less than 0. But in this Hilbert transform, what exactly we are multiplying minus j with signum. So, your spectrum for signum will be look something like this. The positive frequency is multiplied with minus j amplitude and negative frequency is multiplied with the plus j amplitude. So, here now if we try to do the same thing with the cos signal. So, if this is a cos omega ct, so the positive, this is a positive frequency which has amplitude a by 2. So, we are multiplying with minus j. So, that will be shifted from real plane to the imaginary plane, and the amplitude will be minus j a by 2. Similarly, if for another negative frequency, what it happens that you just multiply with plus j, that is a plus j a by 2. So, if you just multiply a by 2 with plus j, then you can get the cos is converted to the sine. So, what is that is the Hilbert transform, which will add the 90-degree phase shift, and it will easily distinguish the we can see that it has also advantage that you are moving from real plane to imaginary plane. So, until and unless we do not move from real plane to imaginary plane, we cannot distinguish the difference between the image and the actual signal, and this is a mathematically we can have an advantage by using a Hilbert transform. You can easily distinguish the positive means desired frequency and the image frequency. Same thing we can also draw. So, here only carrier is shown. If there is some frequency x omega, if there is some x omega will be there, then there is a shift you can also observe in complete band. So, this is a band here shown, and this is a single tone which is shown here. So, based on this principle, the two architecture, that is a Hartley and Weaver architecture, will work. There is another thing also I just want to add, that when we are transmitting or when we are receiving. So, when we are receiving any signal with a carrier a e raised to j omega c t. So, we already know that a e raised to j omega c t can be written as a cos omega c t plus j a sin omega c t. So, same thing that if you add a cos omega c t, if you multiply the sine with the j. So, when you multiply sine with the j, then this will be added. However, this at the negative frequency part it will be removed. So, whenever you want to mathematically show the single carrier up conversion, we should multiply with e raised to j omega c t. So, you might have done the in MATLAB baseband modulation, and when you try to do baseband modulation, we multiply with e j omega c t, which is a combination of a cos omega c t plus j a sin omega c t, and when we try to down convert, we multiply with cos omega c t and quadrature amplitude, and then we try to add those two. So, this is how we transfer the single tone, means which is on the air. Now, we try to use this Hilbert transform to reject the image in the Hartley architecture, and that is also widely known as the image reject receiver, because it is rejecting the image. The problem of image mathematically you can reject by using this method. So, how exactly it has been done? It is this is a RF input, and then there is a cos function which is multiplied, and there is a sine function which is multiplied, and we need to add a 90-degree phase shift. A 90-degree phase shift can be easily achieved by RC CR filter and addition of these two. So, for we will try to do each step we will try to do, and then we will analyze the how the receiver will work. So, here this is a Hartley architecture. So, mostly Hartley architecture are also known as a image reject receiver, because it is going to reject the image, and we are going to use a Hilbert transform. Now, how Hilbert transform can be added? The input signal is first multiplied with the sin omega LOT, and then it will be 90-degree phase shift, and then it will be added, which will help us to reject the image. We will go through step by step. We will try to plot at A, B and at the output C, how the your plots will be look like. So, there is a, you can see that there is a image signal which is here, and this is your desired channel. Now, in this case there is a, your RF frequency is high and LO frequency is low. So, this is called low LO injection, lower side low LO injection. Your omega LO is less than your RF frequency, and this is a image that is mentioned. Same way at the negative frequency there is a image. So, here this is a desired channel, and this is omega LO, this is let us say input frequency, that is omega C, this is omega C, and this is a omega Im, this is minus omega Im, and this is minus omega C. Now, what we need to do in Hilbert transform, we already have seen when we try to add minus 90 degree phase shift, the positive frequency will be multiplied with minus j and negative frequency will be multiplied with a plus j. And we should also know that your sin omega LO, so cos omega LO, it is a at plus omega c, it is E by 2, and same at minus omega c, it is E by 2. And for sine, this is a real, and for sine it is a imaginary. So, for plus omega c, it is minus E j by 2, and plus minus omega c plus j E by 2. So, now we try to apply one by one. So, at this is a signal at x a omega. So, what happens for x a omega, we will go back at x a omega, you have multiplied with sin omega LO. So, here low pass filter is there. So, why low pass filter is there, we have removed the omega RF plus omega LO. We are not considering the positive frequency, the addition of these two, we are only considering the subtraction. That is why after the low pass filter we are seeing the signal. So, what will happen, that your positive frequency, so will be added, so minus, and one more thing, this is a omega c and this is a minus omega c. So, if you go at the positive frequency, this is a positive, this will be multiplied with plus j a by 2, because let us say if this is a 2.4 gigahertz and if this is a 2.3 gigahertz, then your omega c, it will be like this, omega c minus omega LO. So, the negative part of the LO will come at the 100 megahertz. So, that is multiplied with plus j e by 2, plus j e by 2. So, if we consider amplitude as a 1, in this example if we consider amplitude as a 1, then this is multiplied with plus j by 2 and the image is also multiplied with plus j e by 2. Now, when we consider the omega c, when it will be considered omega c, let us say if this is a minus 2.4 gigahertz and this is minus 2.3 gigahertz and this is a plus 2.3 gigahertz. So, this plus when it will come, when minus 2.4, that is minus omega c plus this is a omega LO, that is a minus 100 megahertz. So, we need to consider, we need to multiply with minus a j by 2 and both the places minus j by 2 is multiplied, that is why we have shown it like this. So, this is a the positive frequency, means on the positive side you will multiply with a j by 2 and negative side we multiply with plus j e by 2. So, always remember that if you do not want to confuse, you consider omega c minus either omega LO or minus omega c plus omega LO. So, this will give you the positive frequency. So, which omega LO you should use amplitude, that you will come to know from this equation. So, for this case you should consider minus, and for this case you should consider plus, and for plus minus a by j by 2 will be multiplied and minus plus j a by 2 will be multiplied. So, then 90-degree phase shift. Now, we know the 90-degree phase shift. How to add 90-degree phase shift? Multiply the positive frequency with minus j. So, if you multiply this with minus j, this is a minus j, then this will be positive, that is a 1 by 2, and then if you multiply this with plus j, this is a minus 1 by 2. Same thing, if you multiply this with minus j, then this is a minus 1 by 2, and then this is a multiply with plus j, then it is a plus 1 by 2. So, this is how 90-degree phase shift will be added, and in cos there is a no a difference because it is in real part and there is a by 2. So, when we see the cos function, it is just multiply, and you will see both, this is image and both are at positive. But now the beauty of this architecture will come that when you try to add these two, what will happen, that this image will be cancelled out with this image, and this image will be cancelled out with this image, because here image you have a make it a negative, and because in this both the case image is considered negative, your final output you will only have the desired signal. So, this is how graphically you can analyze that how that your Hartley architecture will work. In Hartley architecture, the important thing is Hilbert transform and multiplication with sin omega LOT. So, first you multiply with sin omega LOT, then apply the Hilbert transform, and then add the signal where the xb omega t, which is multiply with cos omega LOT, and this is a final function that you get. You can also analyze the same thing by trigonometry. We will try to solve with the same thing with the trigonometry. Let us say this is xt, which is as cos omega ct plus ai cos omega imt. So, here what is happening? This is your actual signal and this is the image signal. So, both will be there at the xt. Now, if you write at the xbt, where you do the multiplication with cos omega LOT. So, this xbt, how we are multiplying xt with cos omega LOT, and when you try multiply this, there is a term omega c plus omega LO will also come, but we are filtering out this positive component. We are interested in down conversion, that is why we are seeing the omega c minus omega LO. If you are going to do the up conversion, then you should use a band pass filter and it should transmit the omega c plus omega LO. But in this case it is a down conversion. So, we can write A as cos omega ct, or you can write omega c minus omega LOT plus this is as by 2 ai by 2 cos omega im minus omega LO t. So, this is will be at xbt, it has the same amplitude and half will be there. Then there is a x at where xt is multiplied with sin omega LO t. So, what you will get is minus as by 2 sin omega c minus omega LO t minus ai by 2 sin omega im minus omega LO t. Now, if we consider, we can consider minus as by 2 sin omega c minus omega LO t plus if we consider omega LO minus omega m. So, this if because this is your omega LO and here you have a omega im and here your desired signal, that is a omega c. So, your omega LO is higher compared to omega im. So, this is a higher. So, we can write ai by 2. So, this minus will be plus sin omega LO minus omega im t. So, this is xat. Now, xet, we apply the Hilbert transform. So, Hilbert transform of xat. So, we can get this is we already seen that if we do the Hilbert transform of sin will be converted to cos, that is a minus, we will consider as by 2 cos omega c minus omega LO t minus ei by 2 cos omega LO minus omega im t. So, in this case you can also write cos omega im minus omega LO, this both term will be same. So, when you try to add, so your x y t, which is your output, when you add x b t with x c t, you will get both as, that is as by 2 cos omega c minus omega LO t, and another term also will be as by 2, then it is as cos omega c minus omega LO t, and this image will be cancelled out. So, this is a trigonometric way of solving, that was a graphical way. So, both will come to the conclusion that we can reject the image if we try to apply the Hilbert transform and when we multiply with quadrature signaling. So, this is how Hilbert transform has been used while in Hartley architecture to reject the image, and that is why it is also called the image reject receiver architecture. So, there are other thing also I just want to add. There are two kinds of LO injection is possible. One is a high side LO injection and another is a low side LO injection. So, if you try to do the high side LO injection, your omega LO is higher compared to omega c, that is a carrier frequency. In the previous example our omega LO was less than a carrier frequency. So, you can try as a homework that if there is a high side LO injection, how you can reject the image. So, that is you will get the plus half plus half, and again for sine it will be considered as a minus a by 2 and plus a by 2. So, there is a possibility that while adding or subtracting you can decide based on the high side LO injection or low side LO injection at last when you try to solve the problem. So, this is in low side LO injection your omega LO is low compared to the omega RF or carrier frequency, and same thing you can apply Hilbert transform or sin omega LO and cos omega LT if you multiply. So, this is how it will work. Now, how we can use the RCCR filter in order to achieve the 90-degree phase shift. So, if this is your input signal and if this is the V out 1 V out 2, then you can write high pass filter transfer function V out 1 by V in 1, that is R1 C1s by R1 C1s plus 1, and for low pass filter it is nothing but 1 by R1 C1s plus 1. So, the high pass filter you can write the angle of high pass filter, that is pi by 2 minus tan inverse R1 C1 omega, and for low pass filter the angle is minus tan inverse R1 C1 omega, and when you take a difference of this output by output 1 minus output 2, you will get a 90-degree phase shift. So, same thing in the while drawing we have shown that if RC and CR, if it is added, you will get a 90-degree phase shift. So, instead of adding only 90-degree here, if you try to add on the both side 40-45, then you will get a, while addition you will get the complete 90-degree phase shift. So, same thing whatever I have explained, that is written here, and you can also consider the 5 that is a change in the phase at the signal and the image. Now, we want to quantify the image rejection, and that term is called a image rejection ratio. Now, in this, in order to understand the image rejection ratio, in previous example we have considered that your amplitude and phase are ideal, means you are getting 0 and 90-degree perfect phase shift, but in reality there is a error in both amplitude as well as the phase. So, for one LO waveform, if we express in a sin omega LOT, and other if you express as a 1 plus epsilon cos omega LOT plus delta theta. So, this will tell us the change in the amplitude or error in the amplitude, or this will tell us what is the change in the phase or error in the phase. So, if there is some deviation in the phase of delta theta or amplitude as a 1 plus epsilon. So, you can write same XAT as a signal by 2 1 plus epsilon cos omega c minus omega LO plus delta t. So, there is a big equation that you can write it down, and same thing. So, this here this will come like this, and there is a for image A I m by 2 1 plus epsilon cos omega m minus omega LOT plus theta m plus delta theta. So, A signal t again you can write A signal by 2 plus 1 plus epsilon cos omega c minus omega LT, and this is a X signal, and which has a both image and signal. So, the final image you can also write image amplitude, which is a I m by 2 1 plus epsilon cos omega I m minus omega LO plus phi I m plus delta theta and minus I m. So, same thing you can write it this as a, this is a image omega I m minus omega T plus phi I m. So, if you try to define the image rejection ratio, that is called image to signal ratio at the input side divided by image to signal ratio at the output side. So, the difference between this will be given as a image rejection ratio. So, if we consider the average power of vector sum, so if there is a signal, if there is a vector sum A cos omega t plus alpha plus B cos omega t, then we can write the average power. So, this is a some vector sum A cos omega t plus alpha plus B cos omega t. You can represent the average power in terms of A square amplitude, which is this, plus 2AB amplitude of A and B, and this is a cos alpha plus B square by 2. So, in the previous equation, if we try to add these two, if we try to add these two, we will get PIM image signal divided by P signal, which is out, equal to AIM square. This is the amplitude, that is 1 plus epsilon square, and this is a delta theta. At other side B is equal to 1. So, that is B is 1, this is 2 1 plus epsilon cos delta theta plus 1, and for A signal it is a positive. So, this positive and negative is coming because the image has a negative and this has a positive, this is a multiply. It is A signal by 2 1 plus epsilon cos omega c minus omega LO t. So, because here it is a positive and there is a change in the amplitude is given by 1 plus epsilon, and this is a delta theta, which is a phase difference. We can directly write it down, the A image square 1 plus epsilon square minus 2 1 plus epsilon cos delta theta plus 1, and AIM square is a common. So, if this AIM square and A square signal is a image to signal ratio at the input, and if this is a image to signal ratio, PIM by P signal is image to signal ratio at the output, you can observe this is a image rejection ratio and there is a positive term at the top and negative term at the bottom. So, we want image to image rejection ratio should be as high as possible, that is our requirement. In reality, we should have a image rejection ratio which is as high as possible, and if you know the phase error and the amplitude error, you can calculate the image rejection ratio. So, what are the drawback of Hartley architecture? The drawback of Hartley architecture, there is a amplitude and phase mismatch, there is a limitation in the RCCR filter and the problem of voltage addition, and so this mismatch will also be there. So, we need to while designing the Hartley architecture, the important term is your amplitude and phase mismatch. You should be careful because it will increase the image portion in your received signal. So, your image rejection ratio will be poor. So, in order to get the sufficient image rejection ratio, your RCCR filter should not have that much mismatch, or you can use some other active method to add the 90-degree phase shift and reduce the image rejection. Thank you. This is about Hartley architecture. We will discuss about other architecture, that are the Weaver and other remaining architecture, in the next class. Thank you.